Hello everyone, my name is D. Mohit Chaudhary and here we are going to talk about the 3D Smith chart from theory to experimental reality. And let me give you some historical context. A Smith chart was primarily developed, extended and refined by Philip Hager Smith between 1939 and 1969. Philip Smith was born in 1905 in Lexington, Massachusetts, majored in electrical communications at Tufts University and joined the radio research department of Bell Telephone Laboratories in 1928. And around in 1930, while employed at Bell Telephone Laboratories, Smith started his work on the diagram that became the Smith chart. Then he later submitted the initial version of his diagram to Electronics magazine in 1937. It was finally published in 1939. In 1940, the MIT Radiation Laboratory started to use the chart. Then Smith published a second article which incorporated further improvements, including the use of the chart with either impedance or admittance coordinates. Okay. Now, if we got to see the theoretical foundations, the Smith chart is limited to passive circuits with positive resistance or conductance with the unit circle, circuits with negative resistance or conductance common in active circuits are not covered. In 2006, IEEE Microwave Magazine presented an article discussing the drawings by M.C. Escher, including a spherical self-portrait highlighting the connection between Escher's drawings and hyperbolic geometry, then emphasizing the connection between Smith chart and Mobius transformation in the 2D complex plane. Zelli proposed an intuitive spherical Smith chart drawing on a ping pong ball in an effort to create a unified chart for both active and passive microwave circuits. However, this drawing lacked mathematical rigor as acknowledged by author, with no equations provided for its construction. Inspired by Zelli's drawing, spherical Smith chart became theories were proposed in subsequent works, where circles in 2D were mapped to different curves on spherical chart or distorted into ellipses in 2D. And now a single equation which was proposed to map the entire reflection coefficient rho plane onto a unit sphere. Yes, the equation involves the real and imaginary parts of rho, normalized impedance Z, resistance R and reactance X. And now rho Z equal to Z minus 1 by Z plus 1. That's one we used in 2D aspect. Now rho in 3D becomes where rho is equal to rho r plus I rho j, okay, equals to 2 rho r by 1 plus mod rho square plus 2 pi into 2 pi. Now this is one equation, and these two equations that we see here are the ones proposed. Now these equations ensure the invariance of circles and angles on the 3D Smith chart, which includes both active and passive microwave circuits on a single sphere. The original Smith chart is mapped onto the northern hemisphere, while circles tending to infinity on the extended Smith chart become circles in the southern hemisphere. The northern hemisphere represents circuits with positive resistance, while the southern hemisphere represents circuits with negative resistance, with east for inductive circuits and west for capacitive circuits. Okay. Now on the 2D Smith chart, the reflection coefficients with high magnitudes of infinity are scattered in all directions, where they are indicating loads with negative resistance. However, on the 3D Smith chart, surpassing the unit magnitude of the reflection coefficient corresponds to moving south, while infinity is represented as a point on the sphere in the south pole. The leading equation presented by Smith as given in 1 is described as a bilinear conformal transformation in his work. However, the global geometrical properties of these transforms are not fully disclosed in his previous publications. This equation maps the constant resistance R and constant reactance X grid lines of the right half plane R of the impedance plane with unit circle of the Smith chart into arcs and circles. Meanwhile, it leaves the left half plane where R is less than 0, negative, to be mapped in its exterior, while also throwing points to infinity in all directions. Contrary to the classical Smith chart literature, which typically considers this equation as a bilinear or conformal transformation, it is viewed here as particular case of inverse transformation, specifically the direct inverse. Direct inverse, also called as Mobius, and indirect inverse transformations are the only types of transformations that map all generalized circles at simple or infinite extended into generalized circles regardless of their position on the complex plane. When points are thrown to infinity, the complex plane, which is in union with infinity set, is compressed to a Riemann sphere in order to visualize them. Now, the equations for the direct inverse and indirect inverse transformations are as follows. The first one is for direct and second one is for indirect. And these equations define the transformations used to map the complex plane onto the Smith chart, allowing for visualization and analysis of microwave circuits. Now here are some differences between 2D and 3D Smith charts, which is very important for us to know. The property on one side and difference on other side. Like you can see here, the positive resistance is described in interior of unit circle, whereas for 3D Smith chart it's on the northern hemisphere. Negative resistance is on the exterior for 2D and in southern hemisphere for 3D. Perfect matching is at the origin, and for Smith chart, 3D Smith chart is in north pole. And like this, these are the differences which you can go through. And let me show the comparisons that the properties showed before. And the 2D Smith chart is on this side, like the normal one 2D circle, and here is the perfect loading, and here on the outside we have all the negative resistance values, negative impedance values, and inside we have the positive impedance values. Whereas this on one side is the earth, which this is just for showing the analogy, and this is the 3D Smith chart inspired from this. Now for the 3D Smith chart, here is the open circuit, the perfect load, the infinity point, null, and here on the other side it is the short circuit. It is the 100% resistance one, means here it is the open circuit, here it is the short circuit one. These are the pictures once you need to observe. Now we will look at construction of 3D Smith chart. This is one abstract way of telling it, but if you see here, now in order to match the desired network, one has to intersect the R equal to 1 or G equal to 1 circles which pass through the origin of Smith chart in figure 6, or through the north pole of 3D Smith chart. When the north pole is reached, matching is achieved. The matching procedure is identical to that used in 2D. The designer simply has to move on the constant R and constant G circles, or on the constant reflection coefficient circles, in order to intersect the R equal to 1 and G equal to 1 circles in the fashion desired. Now as described here, this is the R equal to 1 circle and this is the G equal to 1 circle, and all the circles equations brought together, we can observe the 3D Smith chart here, whereas this is our 2D one. Now this is another representation of how we map the networks to Smith chart. Okay, and here we have a series inductor with a series short stub, and here is a capacitor in a series, and these two are the same, capacitor and inductor in shunt, where one is the shunt open stub and one is shunt short stub, and these are the representations of the same impedances pointing on the 3D Smith chart. On the 3D Smith chart, the orientation is best visualized as the viewer were a person who is walking on a surface with their feet on the circles. Now what are the future developments in this aspect? The future developments in 3D Smith chart focus on integrating advanced computational techniques and enhancing user interfaces for greater accessibility. means because we need a software to render the 3D Smith chart, and it cannot be done on paper with using a software. And their ongoing research aims to expand the chart application scope, including new areas of engineering and emerging technologies like 5G and IoT. And innovations in visualizing technology and software design will enable more detailed and interactive 3D representations, enhancing user experience and analytical capabilities. And the collaboration between academia and industry play a crucial role in driving the evolution of the 3D Smith chart, ensuring its continuous improvement and relevance. And these future developments promise to make 3D Smith chart more powerful and versatile, further solidifying its position as critical tool in engineering. So these are the developments that are going on, and with this we conclude our discussion. Thank you.